Okay, so this is the 2017 question 1, and all I'm going to do is the calculation part because it will be very easy for you just to look up the marking scheme and check the answers to the other parts. So I'm just, as I said, going to go through the calculation part, which is part D. So just like in maths, there are several ways that you could potentially solve the likes of this equation and problem, but I'm going to solve it in the method that I would have taught you in class. So try and follow it as best you can. If you've used another method that works for you, by all means continue on with that method and keep using that. So obviously, anytime any of these calculations come up, what I'd recommend you do is read the question carefully, underline anything important, and just make sure that you're going to try and answer exactly what you're being asked in the question. So this year was a little bit different from maybe other years in that we had to solve this equation from what we call first principles. So it wasn't using your V1, M1, N1, V2, M2, N2, which you can actually use later on in the calculation, but at the beginning we actually had to use first principles. So what is meant by first principles? First principles is going back to the types of problems that we would have done in fourth year, whereby we actually use the balanced chemical equation to help us to solve the equation and the problem, sorry. So I'm just going to write out your equation. 5Fe 3 plus. Okay, so just remembering back to fifth year, what's key in this balanced equation is the mole ratio. So I have 1 mole of my potassium permanganate reacting with 5 moles of my iron. We have 8 moles of protons, which is coming from my sulfuric acid, 1 mole of the Mn2 plus ion, 5 moles of my Fe3 plus ion, and 4 moles of water at the end. So that's the ratio by which they react. Okay, keeping that in mind, I'm going to go back to the information that I was given at the beginning. So at the start of the question, they told me that the compound that I'm working with is hydrated ammonium iron 2 sulfate. Now, as you can see, it's a long, complicated molecule with several parts. You may remember a similar molecule when we looked at our water of crystallization, and you see the full stops, which means that we have water molecules or other types of molecules attached on. So even though I have full stops in here, this is all in fact one large molecule. All of the other numbers and parts tell us the different numbers of atoms of the different types of elements that are involved in this molecule. So the name and the molecular formula in some ways are irrelevant for the start of the problem. So we'll just take it for now that it's a really long molecule with lots of different atoms in different ratios. But what's the key is that I have one of them. So that's one molecule of this compound. They told me at the beginning I weighed out 8.82 grams of it, and I dissolved it into a 250 centimeter cubed volumetric flask. Now, what the question then continues on to ask is, well, what would happen if I then got a pipette and I pipetted out 25 mils of this solution? So just to kind of help you visualize that, I'm just going to draw a pipette. And as I said, what I'm working out is how many moles are in fact in this pipette. So just to conceptualize that problem, I'm weighing out 8.82 grams and dissolving it in a 250 centimeter cube volumetric flask. Then I'm pipetting out 25 milliliters of that solution, and I want to work out how many moles are in this solution. So you can see that this is not your standard V1, M1, N1, V2, M2, N2 formula. Now, the formula that I would have recommended that you use up until this point that is linked into this, I'm dealing with grams, quantities of liquids, quantities of liquids. And obviously, anytime we're talking about these types of problems and I have a balanced equation, well, I'm going to be dealing with moles as well. So I have a really long formula that's probably going to help me in some way here in a second. It's volume in liters multiplied by molarity in moles per liter equals the number of moles, which is also equal to the mass in grams divided by the relative molecular mass. So looking at this long equation, I'm trying to figure out this kind of narrow answer here. How many moles are in this? Now I have figures back here and here, so these are probably what I'm going to have to actually initially work with. So at the beginning I weighed out 8.82 grams of my hydrated ammonium iron 2 sulfate. So I can actually easily work out the number of moles. Okay, now when I say easy, there is a little bit of extra calculation involved. So I'm going to work with this side of the formula here, and I'm going to say the number of moles is equal to the mass in grams, which is 8.82 grams, over the relative molecular mass. Now generally we work with compounds which have simple relative molecular masses. This obviously has a little bit of work involved in calculating it. Treat any of the dots like a plus, and then you add in each of the individual parts, and you work out the RMM of that compound there. Now I'm going to save a little bit of time, and I'm going to tell you that the RMM equals 392. So I'm going to put that figure in here. So now I'm still working basically with this here. I'm just after solving when I get this answer. So the number of moles equals this over this. So the number of moles will now equal 2.25 times 10 to the minus 2. And that's in the flask. Because if you think about it, that's how many grams I dissolved in here. Now, that's just how many moles I have. If I want to solve how many moles I have in here, what I then did was I took 1/10 of the volume of liquid and I pipetted it out into a container 1/10 in the size. So this is a very simple way of solving how much would actually be in here. If that's how many moles I have in this container, well then I'm going to have 1/10 in that container. So I just divide my answer by 10. So therefore, in 1/10 of that, you will have, and it will be, and just putting that into your calculator, 0.00225 moles. Okay, and that's actually pretty much your first answer there. So part 2, so that would be part 1. Part 2 then goes on to ask you about, and I'll just get the question up here, the number of moles of potassium permanganate or manganate 7 required to oxidize this quantity of Fe2+. So now we're getting specific to our reaction. Now this again, as I said, is first principles, and this is using basically this formula along with the balanced equation, and that's what we do or how we do first principles. So in this question, I've just solved that I have 0.00225 moles of iron, which basically means this figure here, 0.00225 moles. Now what first principles allows me to do, and you can do this anytime during chemical equation and calculation, is it allows me to look at the ratio of the molecules, the ions, the compounds that are reacting, and compare them. So provided they react fully, I know that if I have 5 moles of this, I'm going to have 1 mole of this reacting. So in this case, if I only have 0.00225 moles of iron, well then, how much of this would I have in comparison to this? I'm going to have 1/5 of it. So it's actually quite straightforward. If I have this much iron, well then I'm going to have 1/5 of my potassium permanganate. So actually all I need to do with my answer for part 2 is use my 0.00225 moles, divide it by 5, and that gives me 4.5 times 10 to the minus 4 moles. So part 2, you're just very simply using this balanced equation. That question could have asked you anything. It could have said, how many moles of Fe3 plus would I have ended up with? Same amount. How many moles of my Mn2 plus would I have ended up with? Again, it would have been a fifth. Or it could have asked me, how many moles of water would I have ended up with? And in that case, you'd have had to have got 4/5 of it. So again, it's just about being aware that you can link this equation and use it with the balanced equation to solve lots of problems. So that's as straightforward as the part 2 was. Part 3 was then asking you to find the molarity of the potassium permanganate 7. So now I want to actually get the molarity of that. Now what you might have tried to do at the beginning, because we're so used to using it, is using the V1, M1, N1, V2, M2, N2 formula. Now what you can actually do is now use it. You wouldn't have had enough information to actually use it before this, but now you will. So if I use KMNO4, and then I have my Fe2 plus, and I write down all of the figures, so V1, M1, N1, V2, M2, N2. My volume for the potassium permanganate is going to be the titration figure, which they've told me in the question. The molarity is what I'm solving for. Again, read the question if you're not sure which one you should be looking for. They tell you in the question, what is the molarity of the potassium permanganate? Has to be this one. The number of moles from my balanced equation is 1. Over to my iron, Fe2 plus, the volume is going to be the quantity that you pipetted out each time, 25 centimeters cubed. Molarity. Now this again is where you have a small little bit of a side calculation. What is the molarity of my iron solution? First of all, molarity, moles per liter. Moles per liter. If I want my molarity of the iron, let's go back up to what I solved. Up here, I figured out the molarity, or the number of moles that I had in this container here. That was this figure. Let's compare. Number of moles in the flask. Number of moles in the flask. So that was 2.25 times 10 to the minus 2. That's how many moles I have in a quarter of a litre. I can't put that into my equation down here. I need how many I have in a litre. So if I had that many moles in a quarter of a litre, how many moles would I have in a litre? I would have 4 times that figure. So I need to multiply this figure by 4. So it's just a little side calculation up here. 2.25 times 10 to the minus 2 times 4, which will equal 0.09. And that is what goes down here. Okay, now remember, in your equation, V1, M1, N1, V2, M2, N2, this and this are always in moles per litre. So the final figure here, N2, going back to your balanced equation, is 5. And now all that's left to do is to put these into your formula and solve for your answer, and it will work down that the molarity for your potassium permanganate, which you're solving, will equal 0.022 m. Do I have to do anything with that? Absolutely not, because remember, and I've just said it there and I'll say it again, when you solve your equation, your answer comes out automatically in moles, or molarity, which is moles per litre. So that's pretty much that one. That's 2017 question 1. Again, pause at any stage if you're not sure where I'm getting the answers for. What I always think helps is at the beginning, do a little bit of a visualization as to what they're asking. Have your balanced equation, have your formula, and everything therefore is in front of you, and it might be easier to see how do I solve it. Okay? Any more questions on that, just let me know.